Hello, scientists. This is a quick review of Tuesday, May 19th screencast for those of you who couldn't make it or just need a quick review of what we covered. I'm going to go over the Can Crush demo and kind of make some connections to how it relates to air pressure and weather fronts. And then I'm going to go over today's assignment, which is a probability model for predicting weather. So let's go ahead and get started.
Okay, everybody, we're going to do the Can Crush demo. So first things first, here's what you're going to need, or what I have rather, is I got a pan full of ice water, super cold, low energy. I got a Bunsen burner over here, sort of a camping Bunsen burner, I guess. And I have a seltzer water can. It's got a little bit of water in it. And what I'm going to do is I'm going to add a whole bunch of heat energy to this can. When I do that, it's going to go into the water. The water's going to get it really energized, and it's going to go from a liquid into a gas. When it does that, when it turns into a water vapor, it's going to take up way less space, or way more space, and as it does that, it's going to expand inside here, pushing the air out. Now, we talked about heat transfer, and we talked about phase change. So as I'm adding energy, it's going to turn from a liquid into a vapor, and that's going to expand and take up all that extra space in here. Super full of energy. Now what I'm going to do is, once I see water vapor coming out of here in the form of steam, I'm going to take the can, I'm going to flip it over, and I'm going to put it back into this ice bath. Now what that's going to do is it's going to really quickly take that heat energy, and it's going to transfer it from the water vapor, and it's going to turn it into back into a liquid. Okay? So the whole point of this lab is for you to see what phase change and heat transfer has to do with pressure, high and low pressure. Since we're talking about like predicting weather, I want you to be thinking about, while you're watching this, what this might actually have to do with cloud formation, right? What is high pressure? How does high pressure influence the creation of a cloud, right? What role does it have to play with in terms of condensation? What does it have to do with evaporation? Right? So I'm going to heat this up again until I see steam coming out of this can, and then that's an indicator to me that all the air has been pushed out, and all that's left is water vapor. Now, if we're thinking about this, water vapor takes up way more space than the same amount of water if it were in the form of an ice cube, right? Like an ice cube, you know the size of an ice cube. If we took all of that water and we superheated it so it went through the liquid phase and then into the gaseous phase, the space that water vapor takes up is way more than the solid or liquid phase. So right now what I'm doing is I'm heating it up. I can hear it boiling in this can. And as I do that, I am pushing out all the air because of the vapor that's now filling the top part of this can. And once I put it into the ice bath, I'm going to switch the heat transfer, and it's going to go from the hot steam into the cold water, and that steam, that vapor, is going to turn really quick back into a liquid. Okay, so here we go. You ready? Awesome. So, what I want you to think about is what role pressure might have, high or low, along with weather. Thanks for watching, everybody. Happy science.
Alright, so now that we've watched the demo again, let's do a quick review of what density actually is. So what do we mean when we talk about density? So for this example, we're going to just call them water molecules. So I'm going to draw this little box, and we'll say we have 5 water molecules in this box, and we'll say they are at room temperature. So these molecules are bouncing around inside of that box. Now, if I change the temperature of those water molecules, something's going to happen. So I'm going to make them red, as if I am heating them up. So as I heat them up, a couple things happen. First of all, they gain energy, they spread out more, and they start moving faster. So now, instead of taking up that original box, they take up the space in the second box that I made. So the water molecules spread out as we heat them up. So we've got the same amount of molecules as we had before, except now they take up more space, meaning they are more spread out. More spread out means that they are less dense. So the density of the molecules in this box is less than the density in my room temperature box. So now let's say we do the opposite. Let's say we cool off those 5 water molecules. The opposite happens. They lose energy and they group together more tightly and they start moving slower. So here we have the same amount of molecules once again, but these molecules are much less spread out. They group together tightly, which means they are densely packed and they take up less room. So when we see them close together like that, they are dense. When we see them spread out, they are less dense. So next we got to look at kind of how this relates to air pressure and weather that we've been talking about. So let's go back and talk about that can crush demo again. What actually happened there? Well, basically, as the water vapor inside the can got heated up, it became less dense. So those vapor molecules in there, they spread out. Basically, they pushed a lot of the air that was in there out, and the water vapor spread out and took up all of the volume inside of that can. So we had low density water vapor inside of that can. So then we had the ice water. And when we suddenly cooled off all of those water vapor molecules in that can by putting the can in cold water, well, we forced those molecules, that water vapor, to suddenly condense. Well, in that demo, that little notability demo I just showed you, we saw that when you cool off molecules, what do? They get closer together. And so as that happened very quickly in the can, well, the can imploded. We crushed it. Those molecules suddenly squeezed together and they took the can with it because the top of the can was under the water. So basically, as those molecules moved together, the can got sucked in with them. So what does this mean for weather and climate? Well, this difference in pressure happens in our atmosphere, although it's not quite as extreme. I wouldn't expect us all to get crushed by sudden change in pressure. That'd be terrifying. But what does happen is water vapor gets heated. It becomes less dense like it did inside of that can. And we know that warm, less dense air rises. And this is because of that difference in pressure. And that difference in pressure was really, like, in an exaggerated way, it was really shown in that can crush demo. You were seeing right there an example of a difference in pressure. So that difference in pressure is what gives us these high and low pressure systems. And as we know from our last lesson, when we have a low pressure system, we have that warmer air rising where it then cools and condenses. So this is kind of the connection between that can crush and our weather. We get differences in pressure, which causes differences in density. Warm air tends to rise because it is less dense. It is moving from an area of low pressure, from an area of higher pressure to an area of lower pressure. And this is why we get low pressure and high pressure systems. All right, so next let's take a look at today's assignment. So I'm going to go into my distance learning folder, go all the way to the bottom, and you will see predicting weather, explore 2, probability calculation. You're going to go ahead and open that up like normal, and you're going to want to send it to Notability so that you can work on it. So once you've got this in Notability, you're going to see that it is a 2-page assignment. The first page has some questions. Those are on you to complete. And the second page is this, what we call the spaghetti model. Let's take a look. So this is a model of a hurricane. The hurricane is that little black swirly looking circle at the bottom. And all of these different color lines are predicted paths that meteorologists say that this hurricane could possibly travel on. So if you count them, you should come up with 14 of them. So we got 14 possible paths. So if we wanted to predict the probability of this hurricane hitting you where you are, we'd have to look at where you are, and then we'd have to see, well, only one of these paths cross there. So let's look at Florida, for example. Florida is that state in the lower right here. So I'm looking at it, and I see that only that blue line goes through Florida. So that would mean that there is a 1 out of 14 chance that this hurricane is going to actually hit Florida. So that's not a very high probability. Those people are pretty safe. I could look at another state and let's say, Oklahoma, the old panhandle up there. I could figure out the probability by counting how many of those lines cross through there. So I see, the green one, the brown one, the purple one, the light blue one, the light brown one, the pink one, the gray one, and the red one. So there's a lot of chances. There's a lot of different paths that could take that hurricane right through Oklahoma. So you would do the same thing with that. You'd say, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. So there is a 9 out of 14 chance. That's the probability. 9 out of 14 chance that that hurricane is going to hit Oklahoma. So then I'd take 9 divided by 14 and I come up with 0.64, which is 64%. So there's a 64% chance that that hurricane is going to hit Oklahoma. Ooh, that's not great for the people in Oklahoma. So this is how you calculate the probability. You guys have a couple questions that are going to ask you how to do that, or ask you to do it for specific states, and you're going to have to look at specific states. If you don't know all the states on a United States map, feel free to find a map online, and it might be a good idea to memorize those. It's handy stuff to know. If you guys have any questions or you need any help, please feel free to reach out to me, and we'll talk to you soon.